There was a question. Is there if there is robustness when we are optimized?
So we do not robustly optimize. That is a little bit like robust optimization is a little bit more computationally challenging. And since we are kind of constrained by laptops usually, I do not want for you to load 27 proton doses at the same time when and I don't know if everybody of you has 32 or better 64 gigabytes of memory on their laptop. So it becomes a little bit challenging to do this live, but I will try with an example of the new Matrat version later. But so we can kind of simulate a shift of the patient now. So for that, I removed this auto checkbox next to the ISO center so that I can manually change it. And I change it to, let's say in X, let's be substantial. Let's give it a 5 millimeter bump. And let's also in Y direction or in Z direction, let's move everything by 5 millimeters. Just let's be a little bit, let's be dramatic. So someone really messed up while positioning. So we are moved by 5 millimeters. And you see this now basically that the X has moved quite a bit. So it's quite in this lower part here. And with this, what we do not click optimize. It should be gray anyways now, but we recalculate the dose for the shifted ISO center. Let's hope that this works. Sometimes I'm really not that sure. So, and this is the recalculated dose. And what you see here, maybe I can zoom a bit, is that we really now have a horrible hotspot here where kind of the Bragg peaks shift into each other. There was kind of this Bragg peaks that were here that suddenly saw lung instead of tissue of the liver. They now just shift basically into the first tissue that they observe here. Yeah, because, well, now I zoomed way too far in. Yeah. So you really see this here, like Bragg peaks that were here were shifted 5 millimeters down where they did not pass the liver tissue here. So they end up depositing all their dose here. Yeah. So you see that this is quite a big problem. And for photons, you can try this out by yourself. For photons, when you do that, what happens is that kind of the dose shifts. Yeah, so the dose will be moved, but it will not look as inhomogeneous. Yeah, for photons, the dose is much more static when we shift it under uncertainties, which makes it much more robust. And you also see that the safety margin here didn't really help us. Yeah, it was I think it is even a 5 millimeter margin, but it doesn't help us. Yeah? It's basically the dose here is extremely underdosed here, and it's extremely overdosed in this corner. Just because we have this problem of peaks shifting into lung tissue where nothing is stopping them and to the border. So you see, maybe a proton liver treatment is not as easy and straightforward of just switching to protons, but you really need to think of how do you do your positioning and how you verify that the tumor is where it's supposed to be. Yeah? So with great precision, with these great Bragg peaks, comes great uncertainty in depth. Yeah, but it comes from a lot of things. Like it doesn't come, it's right that basically with the physics, we are actually quite good. So we can say, if we know what's in the beam path, we know where the Bragg peak is. But the problem is really, first of all, the imaging. It's also you image with a photon scanner, like you image with a CT. A CT is like low energy X-rays. Yeah, it's like keV range. This gives you an attenuation factor, which you can relate to electron densities, but this does not tell you which materials are there and whatsoever. So you already have an inherent uncertainty due to that. People try to get around this by using dual energy CT, so they get a little bit more information about the tissue in there. Or there's like even the idea of using, there are also some products doing this. You could do a proton CT, for example, but protons are not very nice to do tomography with because they scatter. So they scatter quite a lot. So the images are not as well resolved. So it's an imaging problem. Yeah. It's a problem of the image that you do for planning. It's a problem that you don't have an exact image at the time when you are irradiating. You saw this MR Linac, like for photons, you can try to integrate an MR. There's also a big project in Heidelberg trying this for protons. There's also other projects and other proton centers and ion therapies trying to do that. But like think about integrating, like shooting protons while there's MR and magnetic field active might also be like not helping you to be certain about where the proton beam is going. Of course, you can calculate this, but then you have maybe field inaccuracies. There are slight fluctuations or whatsoever. So like the field is maybe not completely homogeneous. You need to know your field very well and so on and so on. It's like really, it's an imaging problem and that you do not have an image exactly when you treat. And if you have an image exactly when you treat, it's not a good image. It's maybe a cone beam CT image, which has worse image quality even than a CT, and so on and so on. So there are multiple problems where this uncertainty comes from, and combined with the physics that we have at play, namely the high dose peak at a specified depth, we get like an uncertainty problem. Yeah, it's kind of a combination. I think it's generally a rule when you can be very precise. Usually this precision, you usually only achieve this precision when you know all your conditions very well. Yeah. And since you are not so knowledgeable about all the conditions and have a high sensitivity then to the conditions changing, you can end up with large uncertainties. So that's like one of the things to consider. Like if the last 15 minutes, I can do like a short overview of how to tackle this. On my computer should be able to do one robust treatment.
Excuse me, I have a question.
Yeah.
How did you zoom in on it's a technical question, zoom in on the ISO center?
Yeah, you can zoom in by using these zoom buttons on top here.
Yes, yeah.
Yeah, so you basically just select one of them and kind of can mark the region, and then you can zoom in. You can zoom out again. Always forget how to reset the zoom. I know it works there's a way to reset the zoom to its original state, but I have to admit I forget this, and then I start, probably it was this. Yes, was clicking refresh. Okay, so this is basically our dose problem. Here, now I have changed, it has also changed the window, so this is really a severe hotspot. Remember, we planned for 3 gray, and now we have 5 gray in this region here. It's really severe. It accumulates in this one spot where suddenly there is tissue again, and like spots that were before then, that went to tissue before, then going to lung now here. So basically, this can have very unintuitive effects in a way that you don't kind of capture or don't think about manually. Yes, I just said like the scale just changed. So that's really, we go up to 5 gray here while this is still 3. So if you change the scale, you might also mistake this. Like if your scale is still 3.2 here, then it looks like this, right? So it looks black, but it doesn't look so bad. But it's just because you are not scaled well enough. So this hotspot is really, really severe. Okay, good. Now, let's do for the final interactive part that we can do. Let's switch to carbon ions. You can very easily switch to carbon ions as well. We can use the same gantry angles for carbon ions. So you basically, if you did this exercise with me, just click auto again next to the ISO center. So it hopefully will find itself or reset itself again at some point. No, it doesn't want to reset itself right now. Why doesn't want it to do that? Let's try it. I don't know, something is broken in the background. I will probably just restart quickly. My MATLAB, not my MATLAB. I will just remove certain things. Well, let's just try to load again. Now it worked. I don't know why it didn't work before. I hope it works for you. If not, just restart quickly. So we set the auto again. So our ISO center is now finally nicely in the center of the tumor again. And we just switched the radiation modality to carbon ions. I want to find the ISO center again. There it is. So we switch here to carbon ions. And something was mentioned before in the chat as a question, the type of optimization changes. So what you see here is that the type of optimization becomes LEM4 underscore RBE weighted dose. Okay, what does this mean? The problem is for ions, in the rest of the symposium, this was probably discussed, but like heavier ions than protons have a very strongly depth-dependent radiobiological effectiveness because their linear energy transfer, maybe because, or at least the linear energy transfer is correlated with the depth. So it increases with depth. Yeah. And what people figured out is that localized dose distributions, how locally energy is deposited, which is related to the particle property of linear energy transfer, is changing the way the tissue reacts. And so I said it before, the same dose of carbon ions does not do the same thing as the same dose of photon ions. There's a lot of physical research avenues down this way since, so you can look into microdosimetric quantities if they relate to that, or nanodosimetric quantities. But in principle, you need to apply a biological model that models this change in depth of the biological response. And this model that we have here is called local effect model, LEM4. So it basically tries to derive local dose distributions on the small scale and how they relate or what they would be equivalent to on a macroscopic scale, and then creates basically a model of the effectiveness. There's two ways. There's actually another setting you can choose, and this was a question. You can say effect or RBE weighted dose. So when you work with biological models, you have different ways for what you optimize. So there's different ways to do that. I will not go into too much detail, but you could optimize directly on the RBE weighted dose. This makes the equations a little bit not nice. Or you could optimize on the exponent in the linear quadratic model equation, which is e to the power of minus alpha times dose minus beta dose squared. You can just optimize this linear quadratic term, and that's what you do when you do LEM4 effect. But I will not go too much into detail there. So now then we have switched to carbon ions. We can just do the same workflow again. Yeah, we will now calculate ion dose, and this will take a little bit longer because we need to incorporate these biological models. If you are a MATLAB user and look into this one data structure that stores the matrix, you will actually observe, let me quickly go there, that here in this data structure, where we before had this matrix for the dose, you also have matrices for alpha dose and beta dose, which are the linear quadratic components. Yeah, basically this is alpha times dose. It's a kind of big matrix with 6,000 or 7,000 beamlets. And you have the, sorry, here it is. You have the beta related dose and so on. So there's more information to be computed to incorporate this kind of biology. And then you click optimize, and we can check out or learn a little bit about the physics and the result of an ion beam. And you see now the optimization becomes also a bit slower. Yeah, needs to wait a bit, needs to, like, every step of the way takes a bit longer. So there is maybe a question in the chat popping up. Yes, this is also interesting. So if you you see these spikes in the optimization. So this is now really, for that you need to understand what the optimizer does. So the optimizer that we use is an interior point optimizer using a quasi-Newton method. What does that mean? Basically uses the Newton method to find the root of the gradient. Quasi-Newton means it spares a little bit of memory there. And interior point means it includes a barrier function. What is a barrier function? So what we need to have realistic plans is we cannot optimize or cannot find solutions where beam intensity is smaller than 0. Right? The beam intensity smaller than 0 means negative dose, and this doesn't work. So what you can use to have like these boundaries, let's discuss this. Maybe because if someone's interested, I will not stop their interest. What happens is, or how you can do this to ensure this positivity is that you add a barrier function on all the intensities, which is a logarithm. Yeah. And you can scale this to make the barrier very strong so that it already pushes you away from the barrier when you far above 0, or you make the barrier a little bit weaker in a sense that kind of it only gets active in a sense when you're very close to 0. And these spikes here are often cases of this barrier function changing, yeah, or getting rescaled. So basically, if you rescale, then you suddenly might be able to do a very far. You might basically get sent back far away from 0, and then kind of your objective function value spikes until it finds again. So it's kind of just inner workings of the optimizer, and it's very unusual to see this if you are accustomed to, for example, conjugate gradient descent, where it kind of reduces all the time. But here it's like really, it's just like this barrier for non-zero-ness in a sense that is changed here. Doesn't have any bad effects. It's just kind of one feature of the optimizer in the way. And now you see a carbon plan with the same settings as the proton plan. Of course, we have reset the isocenter, reoptimized, so there's no big variations. If we would now do the same shift that we did before, of course, we would have the same problem as the protons because carbon ions have the same precision thing going on. So if we have a shift and we shift out of dense tissue into air-like lung, we would have the same problems. So the same considerations apply, but on top of all these physical considerations, we now have the biological considerations. You see directly that our system here shows RBE weighted dose. Yeah? And if I look at a dose volume histogram for this patient, it looks really nice. One thing to see is slightly increased hard dose. Yeah, we have again hard dose for the initial proton plan. We had almost 0 hard dose. Yeah. So there's a little bit of stomach dose as well. And this comes from the fragmentation tail. Yeah, so basically when carbon ions pass through matter, it can happen that they fragment, and it will happen at some point for most of the ions, for many of the ions. And then they have lighter fragments and they have a different range. Yeah, basically because their atomic number is different and whatsoever, and there's quadratic dependencies in these, and so on and so on. The range changes. They have a bigger range. They lose energy more slowly per nucleon. So you have this fragmentation tail where these particles then lose the rest of their energy. Yeah, for example, we have an interesting project at the moment which follows the theory that you put helium ions and carbon ions in the same beam, which you can do because you can accelerate them at the same time due to their relation of atomic number and mass. So and helium ions in such a beam have 3 times the range. Like if they have the same energy per nucleon, they have to say 3 times the range. So this is kind of related to why here this fragmentation tail you see kind of decaying towards the distal edge. And this means like should be a little bit of planning. The dose is very low in the fragmentation tail, but it needs consideration. Still, yeah, these dose volume histogram here look really good. But the most interesting part about this is let's now turn off, or let's look at the actual physical absorbed dose, energy by mass. So what I would like you to do is here on the right side, click on like just lock the scale, like this lock settings locks the scale in place. So this scaling here from 0 to -3 point something doesn't change. And now I switch here in this display option from RVE weighted dose to physical dose. There are still some other beams left over from the photons, I guess. I need to probably fix that these get deleted. But let's just switch to the physical dose and see how much lower it is. Yeah, the absolute, like the energy deposited per mass is much lower than it was needed to be for photons to achieve the same effective dose. Yeah, so in principle, I can zoom in a little bit. Then you also see really nicely that there is a change in depth. Yeah, so basically both beams come in from here. So the physical dose is the energy dose, energy absorbed in mass is lowest here. So it has a value of around, like physical dose is almost like 1/3 of the actual prescribed dose of 3 gray, I think, per fraction, which you see here. Here it's also a little bit lower. Maybe we can check it out here. So there's the RBE weighted dose. No, it's actually quite good. Here it's 3.1. So a little bit overdosing. But the physical dose is really nearly 1/3 of that. So we have an RBE for these combined beams of 3. Yeah, this is kind of substantial value, and it's different to the RBE in the entrance dose or in the entrance region here, where the physical dose is a little bit higher. So problem is we have 2 beams, so it's not that descriptive. But here the physical dose is 1.5, so the RBE is lower. Yeah. So this means this model in depth, like I encourage you to just plan a carbon beam in box phantom or something like that with 1 beam and just look at how the depth dose and the physical dose looks like. You see that this is like a really strong effect. Yeah, there's a question.
Does the method provide the LET calculation or optimization for proton and carbon?
I think I answered this very early. So you can calculate LET in MATRAT, especially in the new version that will be out soon, probably beginning of November. You can calculate LET. We have LET optimization in development. So there's at the moment a contribution of one of my students. If you go on MATRAT, this is, I think, MATRAT, and you go here. So you see that there's currently 2 things. There is a new release contribution. This will be the next release. And there's also like here a contribution by a student of mine who did like comprehensive LET optimization. So this is soon in there. In principle, you can also play around with that result. You can already, I think, now calculate the LET, but you cannot do anything with it.